So let's see, what did we learn last time? Let's get this going up on the screen and kind of review where we're at with this unit. So let's go to our grade screen as usual. Oh yeah, we did the rational root theorem, Descartes' rule of signs, fundamental theorem of algebra, or the factor theorem, the remainder theorem. Yeah, we've gotten into all the fun stuff. We did polynomial long division and synthetic division. So this week we have solving polynomial equations, which probably uses all this stuff we've learned up here. A quiz and graphing polynomial functions. So all three of those this week. Which means next week we'll take our test and be done with this unit. But let's see what we can have. So this one's pretty much going to be pulling together what we've learned in the first 4 lessons. Close module 2. We don't need that one. Here we go. Solving polynomials. Solving polynomials. What theorems can be utilized in solving polynomials? And they're depressed equations. No, they're not sad, but we call them depressed equations. Just yeah. How can polynomial functions be written when given the zeros? So you were introduced to algebra at a very young age. In elementary school, they probably had something like this. Fill in the box. Something plus 6 equals 10. That really is algebra. But sometimes they just put a little space there. Space plus 6 equals 10. So later on, that turned into a variable, usually x. We'd say, okay, instead of just a blank box, we're just say x. So tell me what x is. Then you moved up to 2-step equations. Well, now we got like 2x plus 6 equals 10. So you had to do a little bit more work. Then we got to 2x plus 3y equals 10 and x minus y equals 8. And we had to do those systems of equations that we did back at the beginning of Algebra 2. And then we got to quadratic equations. We had x squared plus 7x plus 12 equals 0. We found out there's 2 solutions to that. And we had to find what those were. We've learned about graphing, factoring, performing operations on radicals, all concepts that help you in one way or another find a solution or solutions for the variable. Now it's time to find the solutions to higher degree polynomial functions. That's what we've been working on this unit. X to the 3rd, x to the 4th, x to the 5th, whatever it is. To accomplish this, you need a strong foundation with the many theorems you've learned in previous lessons. So we're going to, here's all of them if you need to review any of them that we've done the last week. Fundamental theorem of algebra, rational root, Descartes' rule of signs, remainder theorem, factor theorem. But let's take a look at this. X to the 3rd plus 3x squared minus 22x minus 24. Okay, I'm going to write that down. So that was the P over Q, right? So P over Q. All the possible roots, which in this case, the P is negative 24. Or 24. We just put it 24. And this is just 1. So that makes this in a simpler one. We just have 1. So what are the possible roots of 24? 1 and 24, 2 and 12, 3 and 8, 4 and 6. So the possible roots are plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, plus or minus 8, plus or minus 12, and plus or minus 24. Because this could be, negative 1 times positive 24, positive 1 times negative 24, because this is negative 24. They can always be positives or negatives. So we have 1, 2, 3, 4, 5, 6, 7, 8, 16 possible roots for that equation. If you count all the positives and all the negatives. Right. So that's the first thing they did. They broke it down to plus or minus 1, 2, 3, 4, 6, 8, 12, or 24. So there are 16 possible values. So next, we use Descartes' rule of signs. Close that. Descartes. Let's do that. So we said, okay, if we count how many sign changes there are, so this goes positive, 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 negative. There's a sign change. Okay, so there's one sign change. One sign change. So that means one positive uh, rational root or real root, you could say as well. One positive rational root because it only changed signs once. It went from a positive to a negative and stayed negative. So that helps us because we know there's three possible solutions, right? So there's three solutions, and we know they could be positive, negative, or imaginary. I'll just put the I for imaginary. And so we know, first off, there's only one positive root. That's our only choice. Now we got to figure out how many negative roots are there. So remember the way we do that, let's just say this is f of x. So we do f of negative x to figure that out. So if we say negative x to the third power plus 3 times negative x squared minus 22 times negative x minus 24. And we simplify that. Negative x times negative x times negative x is negative x to the third. Negative x times negative x, just 2 times, is a positive x squared times 3. So that's a positive 3x squared. We have negative 22 times negative x, so that's a positive 22x. And then we have minus 24. So it goes from a negative to a positive. There's one sign change. Let's see, this sign change happened right there. Positive to a positive, positive to a negative. So there's two sign changes. Which means there are 2 or 0 negative roots. Remember, anytime there's 2 or more, you got to subtract 2. So that means there could be 2 negative, and there'd be no imaginary roots. Or the other possibility is there's one positive, none of them are negative, and 2 of them are imaginary. So we know it's one case or the other. We know there's only one positive. It can't be imaginary because remember, imaginaries come in pairs. If there's one, there's 2. There's always pairs. So if there's 1, there's guaranteed 1. 2 could be 2 negative, or maybe they're imaginary. So that rules that down pretty nicely there. Okay. So we've done Descartes' rule of signs to figure out what we're looking for. What do they do next? See, that's where they check the sign changes. 2 sign changes are going to be 2 or negative, 2 or 0 negative zeros, and there's only one positive 0. So we've used that. Now use the fundamental theorem of algebra. We already made this as well. Fundamental theorem of algebra says since it's an x to the third equation, there are 3 roots. So we know it's either 1 positive, 2 negative, 0 complex or imaginary, or it's 1, 0, and 2. Now we start testing the factors. So let's start going through them. This is where we use our synthetic division to start narrowing it down. So the first one we're going to check is a positive 1. So we're going to divide by negative 1. Oh, wait, no, we do divide by positive 1. Positive 1 is the root. It'd be x minus 1, but positive 1, we're going to check the 1 first. So with our synthetic division, we just pull the coefficients of 1, 3, negative 22, and negative 24. And we're going to test the root of 1 first. Remember, bring the first one down. 1 times 1 is 1. Add those. 1 times 4 is 4. Add those. 1 times negative 18. Negative 42. 1 is not a solution. How about 2? 1, 3, negative 22, negative 24. Bring that one down. We got 1. 2 times 1 is 2. Add those. 2 times 5 is 10. Add those. Negative 12. 2 times negative 12 is negative 24. That didn't work. It's negative 48. 2 is not a solution. How about 3? 1, 3, negative 22, negative 24. 3 times 1 is 3. Add those. 3 times 6 is 18. Add those. Negative 12, negative 36 is the remainder. Not a solution. So 1, 2, and 3 don't work. Let's try number 4. 1, 3, negative 22, negative 24. 4 times 1 is 4. That's 7. 4 times 7 is 28. That's 6. 4 times 6 is 24. Hey, 4 is a solution. So one of our solutions is x equals 4, which means we don't have to check 6, 8, 12, or 24, at least the positive values. We've already found our one positive solution. Okay, so you don't get ahead of them. Test the factors. There we go. 4. The factor 4 resulted in a remainder 0, so 4 is a 0. So the remaining factors do not need to be tested. So write the depressed equation. It's like, what do you mean the depressed? Is it very sad? No, we've factored out. We know one of the factors now is x minus 4 because x equals 4. So when we divide that factor out, what's left? Now we have x squared, because we started with x to the third, but we factored an x out. So now this is x squared, plus 7x plus 6. We have, this is the depressed equation, which means this is the original equation after we have factored out one of the terms. Now we have a quadratic equation. So we can factor this. Because we take the factors of 6, which is 1 and 6 are 2 and 3. And 1 plus 6 equals 7. So this is x plus 1 and x plus 6. So the other solutions, subtract 1, x equals negative 1, x plus 6 equals 0, x equals negative 6. So now we know our solutions are 4, negative 4, and negative 6. And we're done because that's all there are. There's 3. One's positive, 2 negative. This ended up being our situation. There are no imaginary solutions for this one. There's a positive 4, a negative 4, and a negative 6. That's the nice thing. We don't have to keep doing this with all the negative numbers because once we factor that out, we've got a new equation we can look at. If this is factored out, this is what's left. So what's the factors of this? This times this times this will equal our original equation. So yeah, it's not quite as bad as you think it is. It's like after we found 4, it's like, okay, now do we need to go start doing this? We could have, if we wanted to go back and take the original equation and try negative 1, negative 2, negative 3, negative 4, negative 6, we would have found the same answers. But this is a nice shortcut. If this is taken out of there, what's the other factor? Can we factor that? Yes, we can. Let's see what they talk about here. So they said, write the depressed equation. So when you factored out the 4, you have 176 with the remainder 0. So we put that back into an equation. These are the coefficients, 1, 7, and 6. 1x squared plus 7x plus 6. Say, is it called a depressed equation? No, not because it's sad. It's because it came to the original function but has fewer terms. We depressed it down from an x to the third to an x squared. So the depressed equation can be used to find the remaining zeros. So it took that and says, okay, first thing they did was check the discriminant. That was probably wise. I didn't check the discriminant, but the discriminant, when we do the b squared minus 4ac, equals 25, which is a prime number. I'm sorry, which is a square number. It's not a prime number. It's a square number. It's 5 times 5. That tells us that we can factor it. Since it's a perfect square, the quadratic can be factored. So we look at that 1 times 6, which is one of the ways we can get 6. Negative 1 times 6, 2 to 3, and negative 2 and 3. And 1 times 6 adds together to be 7. So we know that's our two factors, 1 and 6. So our solutions are negative 1 and negative 6. And they tested them by doing the synthetic division with those two numbers. Negative 1 and negative 6 in the original equation have zeros as remainders, which verifies that, hey, that is true. Those are the solutions. If we graph the original function, oh, that's a good one. Let's do that over here on decimals. So the original function was x to the third. Oops, x to the third plus 3x squared minus 22x, and it was minus 24. And if we look at the zeros, the places where it crosses the x-axis, we get those same three solutions that we found algebraically. There's a solution at negative 6, there's a solution at negative 1, and there's a solution at 4, which is exactly what we expected to see, because when we calculated all of that, oh, wait, did I put negative? Oh, I put negative 4. What did I put negative 4 up there? Don't let me write down things that are wrong. We calculated negative 1, negative 6, not negative 4. Okay, 4, negative 1, negative 6. That is what we expected to find as the three solutions, the three places where it crosses the x-axis, the three zeros, because that's what we found down here. We found 4, negative 1, negative 6. There they are. So they show the graph of it there. And then they confirmed it by substituting. All right. When we substitute that number 4 into the original equation for x, you should get the 0 because of the, see, is that the remainder theorem or the factor? That's the remainder theorem. When you substitute a number into the equation, it will tell you what the remainder is. And the remainder would be 0 for each of these because they are solutions. So there's quite a few steps to solving a polynomial equation. That's the tricky part. Look at all these steps it took to get to solve this. But how else are you going to solve an x to the third? This actually narrowed it down. It could have been a lot more work if we didn't have Descartes. It didn't have the rational root theorem, all this kind of good stuff. All right, so we're going to do another one. They have a video of this one. And let's see what they have down here. Another example, solving polynomials. Okay, let's take a look at their video on how they're going to solve this nice x to the third equation.
The first step is to determine the possible rational zeros of the function. You can do this by applying the rational root theorem. For this function, the p-value is the constant term negative 6. The factors of negative 6 are plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. The q value is the leading coefficient of 1. 1 is divisible only by itself and negative 1. Take each factor of p and write it as a fraction with each factor of q as the denominator. Make sure you account for all combinations. These fractions may all be simplified. So, the factors of p over q are plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. The next step is to determine the possible number of positive real, negative real, and complex zeros for this function. You can do this by applying Descartes' rule of signs. First, to determine the possible number of positive zeros, count the number of times the sign changes in the function, reading it from left to right. In this case, there is only one sign change. So, there is only one positive zero of the function. To find the possible number of negative zeros, substitute every instance of x with negative x. Then simplify. Count the number of sign changes from one term to the next. There are two sign changes. This tells you there are either 2 or 0 negative zeros for the function. To determine the possible number of complex zeros, subtract the possible number of positive and negative zeros from the total number of zeros. In the second case, if there is one positive zero and 0 negative zeros, 2 complex zeros are possible. To summarize, the function of f of x equals x cubed plus 7x squared plus 10x minus 6 has 1 positive zero, 2 or 0 negative zeros, and 2 or 0 complex zeros. Next, determine the actual zeros of this function by testing the factors. The zeros of a function represent the values of x that make the function equal to 0. So, replace the function notation with 0. Recall the information from steps 1, 2, and 3. Test the possible solutions using synthetic division and the factor theorem. Begin with the possible positive rational solutions, 1, 2, 3, and 6. Start with factor 1. The remainder does not equal 0, so 1 is not a zero of the function. Keep testing. Now, try factor 2. This remainder does not equal 0 either. Next, try factor 3. 3 doesn't work either. The only positive factor of p divided by q left to check is 6. Uh-oh! All of the possible positive rational zeros have been tested, but none of the remainders are equal to 0. What should be done now? Let's try the negative factors to see what happens. Start with negative 1. Negative 1 didn't help. The remainder is still not 0. What about the factor negative 2? Negative 2 does not work. Try factor negative 3. Phew! Thankfully, the factor of negative 3 resulted in a remainder of 0. Therefore, negative 3 is a zero of the function. An additional benefit of finding this zero is finding the depressed equation of 0 equals x squared plus 4x minus 2. Since this is a quadratic equation, the solutions may be found algebraically by factoring, using the quadratic equation, or completing the square. Calculate the discriminant to make that decision. The value of the discriminant is a positive, non-perfect square integer. This means the quadratic cannot be solved by factoring. Use the quadratic formula instead. Substitute the values of a, b, and c from the function into the quadratic formula. Using the order of operations, simplify the exponent first. Continue the order of operations by multiplying the appropriate integers. Combine the terms within the radicand. Simplify the radicand. Separate the fraction into 2. and simplify each. Go one step further and find the approximate decimal solutions. The remaining positive and negative real solutions have been found. Notice that these two solutions are irrational, which is why they weren't identified using the rational root theorem, but were identified using Descartes' rule of signs. This is another reason why understanding the different theorems is important. So, the three solutions of the equation 0 equals x cubed plus 7x squared plus 10x minus 6 are x equals negative 3. X is approximately 0.45, and x is approximately negative 4.45. Take a look at the graph of this function. Notice that the zeros of the function represent the x-intercepts of the function.
Okay, I was going to look at that as well on Desmos. So graphing this equation that they just looked at, there is the one negative one that we found with the rational root theorem. Now, as you said, the reason we didn't find the others is because they weren't rational roots. We said there'd be one positive root due to Descartes' rule of signs is there's one positive root, but it wasn't rational, so the rational root theorem didn't help us. If we look over here on the positive numbers, 0.44949, and that's rounded. It keeps going. It's not a rational number. It's an irrational number, but it is a positive root. It's a positive number. So Descartes tells us, yeah, there is a positive one and there's two negative ones. But look, this one also is not a rational number. So the only one we could find with the rational root theorem was negative 3. But fortunately, once you find one, it simplifies that x to the third down to a quadratic equation, and we can always use the quadratic formula to find rational or irrational roots or imaginary roots. That's just looking at one that doesn't work quite so nicely, but we can still use what we know to get there. Examine the possibility of sketching the graph of the function example 1. Finding the y-intercept would be helpful in determining the nature of the graph. All right, since all of these have an x in them, when you make x equal 0, they go away. So we know it crosses the y-axis at negative 6, which we also see on the graph. Yeah, negative 6 is our y-intercept there. So figuring out how the graph would look. Let's see. Determine the possible zeros of, here's an x to the fourth minus 9x to the third plus 15x squared minus 9x plus 14. So, and it wants to know what is the p-value. So it's p's over q's, right? So the p-value is 14 for this one, right? That's 14. And so then it's walking us through the steps here. So next, what are the factors of p, which is 14? Type each factor separately in order from closest to 0 to farthest from 0. Well, that would be plus or minus 1, 2, 7, and 14. That's the only numbers that we could use to get 14, right? 1 times 14 and 2 times 7. Right? So it's plus or minus each of those. 8 possible factors for this. What's the q value? Well, it's just x to the fourth, so the coefficient is just a 1. Yeah, the coefficient leading 1. Well, the factors of q, which is 1, negative 1 and 1 is the only way. Negative 1 times negative 1 or 1 times 1. That's it. So if we look at the factors of p and q, the p is plus or minus 1, 2, 7, 14. Q is plus or minus 1. So if we simplify that, just divided by 1, it's still just 1, 2, and 14, plus or minus of each of those. So we found the 8 possible real rational roots. To determine the possible number of real, negative, and complex zeros. So if we look at this, it starts out as a positive x to the fourth. It changes to a negative. So there's a sign change. Goes back to a positive, there's a sign change. Goes back to a negative, there's a sign change. It goes back to a positive. So there are 4 sign changes. It changes 4 times. You got it. This is a great little exercise for you to walk through if you are struggling with this as well. It's right here at page 2. All right, let's go down to the next one. How many positive real zeros exist from least to greatest? Well, there could be none if they're all imaginary, or maybe just 2 of them are imaginary, or maybe none of them are imaginary, and there's 4 real zeros, so they're positive. Submit. Yes, there's either 4, 2, or 0 positive real zeros. Now determine the possible negative zeros. So they substitute negative x in for us. Negative x to the 4th. Negative 9 times negative x to the 3rd. And 15x squared, negative x squared. And negative 9 times negative x plus 14. And they simplify it for us. And we got positive, 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 positive. There are 0 sign changes, which means there will be no negative roots, which rules out half of our choices already. So we've already ruled out half of them. That is wonderful. So how many negative real zeros exist? There are none, because there was no sign changes. Thank you, Descartes, for ruling out half our work already. So how many total zeros exist? Well, it's x to the 4th up here. So there are 4 zeros. So then, considering all the possibilities, how many complex zeros enter from least to greatest? Well, there could be 0, 2, or 4. So all the solutions are either imaginary or they're positive. Oh, I hit the wrong thing. All right, next. Submit. Yep, must be 4 zeros. 0, 2, or 4. Yes. Okay, that was step 2. So step 3, determine the zeros. So the zeros of the function represent the values of x that make the function equal to 0. So you can replace the function notation with 0. Determine the zeros of the function from the previous information, right? We know these possible factors are 1, 2, 7, and 14. We have already ruled out the negatives. It's not going to be -1, -2, -7, or -14 because Descartes already ruled that out for us. There are no negative numbers. There's only 4 possible. So either they're all going to be real, 2 of them are going to be real, or none of these are going to work and they're all going to be imaginary. So it says test the possible rational solutions using synthetic division. Begin with the possible root of 0. Is 1 a solution? If so, what is the depressed equation? So is 1 a solution? So let's play with this one. I want to write it down real quick. 9x to the 3rd plus 15x squared minus 9x plus 14. So we're going to check first off to see if 1 is a solution. So I've got the equation written right in here. If we check 1 and using the coefficients 1, -9, 15, -9, and 14. 1 times 1 is 1. Add those together. 1 times -8. -8. Add those together. 1 times 7. Add those together. And 1 times -2. 1 is not a solution. So it's 1, 2, 7, and 14. 1 does not work. So already we know there are at least 2 imaginary solutions. Remember, because there could be 4, 2, or 0 real solutions, and we know there's not 4. Let's check 2. 1, -9, 15, -9, and 14. Oh, that's a 1. Bring that one down. 2 times 1 is 2, goes there. -7, -14, That's positive 1. 2 times 1 is 2. Negative 7. 2 times that. Hey, 2 is a solution. Okay, so now we know for sure there's 2 imaginary solutions and 2 real solutions. Guaranteed, because we've already ruled out one and found one that's true. So let's try 7. Bring the 1 down. 7, that's negative 2. It's negative 14, it's 1. It's negative 2. 7 is our other solution. We don't have to test 14. It can't be 14. So we need to, let's see, since we know 2 and 7, let's take, when we took 2 out, then we've got x to the third minus 7x squared plus x minus 7 and x minus 2. Since we know this is a factor and know this is a depressed equation, let's take 7 out of this. So if we do 7 divided into 1, negative 7, 1, and negative 7, that's 0, right? And then 7 times 0 is 0. Bring that down, add those together. So the equation we got now is x minus 2, x minus 7. After factoring both of those out, we're left with x squared, no x, plus 1. So if the factors are x minus 2, x minus 7, and x squared plus 1, then our solutions are 2, 7, and plus or minus the square root of negative 1. Because x squared plus 1, if we solve that, you got to take 1 to the other side. You got x squared equals negative 1. So x will be the square root of negative 1, which means this is the same thing as plus or minus I. Remember, I equals the square root of negative 1. So that's our 4 solutions. 2, 7, I, and negative I. 2 imaginary solutions, 2 real solutions. And once I found 2, I could have changed this right here and not take 7 into the original equation. Just skip this one and take 7 into the depressed equation. And once I pull the 7 out of there, I end up with just x squared plus 1. That's how we step through and find the solutions. Let's see what our little activity on Buzz has there. So is 1 a solution? No, 1 was not. Was 2 a solution? 2 is a solution, and we got it narrowed down to there. So since the depressed equation is not a quadratic equation, keep testing the possible solutions to find another one. So they used the depressed equation. After they pulled out the 2, it's like there's no need to divide into the original equation anymore. Now let's divide into what's left. And that's when they found, yes, 7 does work, and then we're left with x squared plus 1. So what's the final 2 solutions? Plus or minus I, because we can take the x squared plus 1, set it equal to 0. It's a quadratic equation. We can solve it by simply moving the 1 to the other side, taking the square root of both sides. So if I is a 0, the function negative I must be because of the conjugate root theorem. It says the conjugate. If you have a complex number like 4 minus I that is a 0, 4 plus I must be the other one. So in this case, if I is a solution, it's 0 plus I. You also have 0 minus I. And if you look at the graph, let's look at the graph of that. Let's just graph this equation on there. It was x to the fourth minus 9x to the third plus 15x squared minus 9x plus 14. Oh gosh, I didn't mean to use a capital X. My caps lock got on by mistake. Let's see if I can just change those to X's and it'll work. Okay, now it's all happy. So when we look at it, woo, boy, let's change the scale to where this doesn't look quite so crazy. Let's do the x-axis from negative 10 to a positive 10. And that's a little easier to look at. We have a root at 2 and a root at 7. And then the other ones are imaginary, so they don't show up when we graph it. So we would only be able to find 2 roots by graphing. We had to do some algebra to figure out the other root. So they're kind of showing the same thing. Complex zeros are not represented on the graph. They're imaginary. When complex zeros are discovered, sketching a graph can be very difficult. The fundamental theorem of algebra indicates there's 4 zeros, but there's only 2 real zeros. So this is an instance where graphing technology will be valuable, but graphing calculators helps a lot there. Recall the conjugate of a binomial is another binomial whose terms are identical but have the opposite sign. Like 3 minus square root of 5 is 3 plus the square root of 5. So the conjugate of 7 plus 10i is 7 minus 10i. Another example in solving polynomials that you can go through. Determine the possible rational zeros using the rational root theorem. This one has 16 possible ones because it's plus or minus. Determine the possible number of real, negative, and complex using Descartes. You find out there's all kinds of options, 4 different, and then determine the zeros by doing the synthetic division. And each time you do the synthetic division, you have a depressed equation. You can use that from that point on until you get it down to a quadratic equation. And then maybe it'll factor, or maybe we have to use the quadratic formula. That's another example. You can walk through that one if you need another example. Let's go to page 3. Now that you understand how to find the zeros, let's write a polynomial function where you're given the zeros. Oh, this is great. Write a polynomial function whose zeros are negative 4, 3, and 7. Well, this will be good. This is like ACT type stuff here. Zeros. Negative 4, 3, 7. That was it, right? Is it negative 4, 3, and 7? Yes, negative 4, 3, and 7. So it's like, okay, they want to know what is the polynomial that has those zeros. Well, it's x to the third because it's got 3 zeros, right? This is not as hard as you're thinking. If there's a zero of x minus 4, that means the factor, I'm sorry, of negative 4, that means the factor is x plus 4. If there's a factor, if there's 0 of 3, there's a factor of x minus 3. And if there's a 0 of 7, there's a factor of x minus 7. Because remember, the way we find these numbers is we set it equal to 0. So x minus 7 equals 0. We would add 7 to both sides and find the 0 is x equals 7. So if we go backwards from x equals 7, we know these are the factors. So if these are the factors, we just have to multiply them together. Let's multiply these together first. So we got x plus 4 times x is x squared, x times negative 7, negative 3 times x, and negative 3 times negative 7. See, all I've done so far is I multiplied together x minus 3 times x minus 7. Now let's simplify this because we have like terms. So this is x squared. Negative 7x, negative 3x combined to be negative 10x. See, we're getting there. Now we just have to distribute the x plus 4 into this parentheses, multiplying these two together. X times x squared is x to the third. x times negative 10x is negative 10x squared. X times 21, 21x. Okay, that's distributing the first term to all three terms. Now let's continue by doing the second term times all three terms. 4 times x squared. 4 times negative 10x. 4 times 21. So next we have to identify like terms. Those are like terms. These are like terms. So let's write it with the combined like terms. So x to the third, there's only one of those. X squared, we got a negative 10x squared and a positive 4x squared. We've got a 21x and a negative 40x. And then we have an 84. This is a polynomial that has the zeros of negative 4, positive 3, and positive 7. So we simply write down the three factors that have those zeros and then just multiply them together. And that'll give us the polynomial they're looking for. You're thinking, wow, Mr. Brock, you do a lot of this stuff and you do it really fast. Well, I'm trying to cover it all in the time material because you can go back and review this in our lesson. You can go back and watch the video and pause the video as often as you need to. I want to make sure to get through all these examples today just to show you. Don't make this real hard. Let's do another one. Let's see. They may have one in the. I like to do the ones in Buzz, so you can go back and review those as well. But if they don't have one I like, we're gonna do another one. But let's see what they end up with. X to the third minus 6x squared minus 19x plus 84. It's exactly what we got. So this will walk through all the same stuff. If you need to go through it slower or look at how to do this, it's all right here in your lesson as well. Important note. Okay, this is an important note because there could be more polynomials. This is the lowest degree polynomial function that could be created with those real zeros. You could include another random zero to create a polynomial function of even higher degree that would still have these zeros, but just have more zeros. Note that the rest of the examples and practice problems demonstrate the lowest degree polynomial function. So we're looking for the ones that have only these zeros, the lowest degree. There could be ones more that have these degrees. Okay, oh, this is good. We're going to talk about multiplicity. So we're going to find the polynomial function with the following roots. Negative 2 that has a multiplicity of 3 and 5. So just before we start the video, though, I'm going to put this on the paper just a little bit to talk about it. If it says the roots or the zeros, negative 2 with a multiplicity of 3, and then 5 is our other one. I didn't write that very well, but that's what it is. Multiplicity, that's an M and a U. Multiplicity, that means really our roots are negative 2, negative 2, negative 2, and 5. That's what multiplicity means. It means there's multiple. Multiplicity of 3 means there are 3 of them. So you're not just doing x plus 2 and x plus 5. I'm sorry, minus 5, because that's a positive. What you're actually doing is x plus 2, x plus 2, x plus 2, and x minus 5. That's what it really is, the multiplicity part. Let's look at their video and see how they handle that. See if they explain that any differently. Make sure you get this.
The first step is to determine the factors of the function. To do that, set each zero of the function equal to x. Rearrange the equation so both terms are on the same side of the equal sign. The factors of the function are represented by each of the expressions involving x, and can be written as x plus 2 times x plus 2 times x plus 2 times x minus 5 equals 0. The next step is to multiply all the factors together.
Which you can multiply together in any order you want to.
Substitute the function notation for 0, and the result is the polynomial function with the zeros, -2 of multiplicity 3 and 5.
Okay, so they just did the work of all the multiplication, but the important part of that is being able to figure out what you're multiplying back together. So if you have -2 that has a multiplicity of 3, make sure you've got 3 of the same factor. 3 of the same factor for that -2, and then there's just 1 5 over there. Oh, and this is one I was wanting. I said I want to find a good example. So good, I'm glad I waited. Roots have 1 of multiplicity 2 and 5i. Oh my, okay, let's switch over to our paper. Okay, so if we have, here's our zeros, or roots, either way. 1 has multiplicity, I'll write it better this time, of 2 and 5i. Okay, they want to know what polynomial has 1 of multiplicity 2 and 5i. And you're thinking, okay, so this is another one has 3 roots, right? 1 and 5i. Because this is multiplicity of 2, remember? There's 2 of them. But don't let it fool you. This has actually got 4 zeros. There's 4 zeros here. You're like, well, wait a minute, Mr. Brock. This only has a multiplicity of 2, so there's only 2 1s, and there's a 5i. How can there be 4 zeros? What have I said over and over again about complex zeros, complex solutions? They always, always, always come in pairs. They come in pairs. So if we have 5i, that means guaranteed we have -5i. It's conjugate. If you have 5i, you get -5i for free. Buy the 5i, get the -5i for free. So you have to assume that. So these factors are x minus 1, because 1 is a solution. X minus 1, because we have a second one. X minus 5i, and then x plus 5i. That is the 4 factors we have to multiply together to find the polynomial that has zeros of 1 with the multiplicity of 2 and 5i. So let's multiply these together first. X times x, x times -1, which is just negative x, -1 times x, which is negative x, and 1 times 1. So that's going to simplify to x squared minus 2x plus 1. Then let's multiply these two together over here. X times x is x squared. X times 5i is 5ix. -5i times x, -5ix. -5i times +5i is -25i squared. Okay, simplifying this, for one thing, this is real nice. Plus 5ix minus 5ix cancel each other out. I need to make sure it looks like a 5. Looks like I'm saying plus 6 minus 6. No, that's a 5ix. These cancel each other out. And this is -25 times I squared. What is I squared? Well, remember, if the I is the square root of -1, and we take that times the square root of -1, because that's I squared, that just equals -1. Square root times the square root means you're squaring it, and it cancels each other out. So this is -25 times -1. So this is x squared plus 25. All the imaginary stuff went away. This imaginary term canceled out by that imaginary term. And this one's I squared, so it's not imaginary anymore. It's actually a -1. So now we just have to multiply these together. X squared times x squared is x to the fourth. X squared times 25 is 25x squared. Now the second term, -2x times x squared is -2x to the third. -2x times 25, -50x. Then just take 1 times both of those. So that'd be x squared plus 25. Like terms, there's only one x fourth, 1x to the third. We have an x squared and 25x squared. So we have 26x squared. We have a -50x and a plus 25. This is our answer. This is the polynomial that has the zeros or roots of 1, that has a multiplicity of 2, and 5i. It also has -5i because that comes as a bonus. Anytime you got one imaginary, you get its conjugate partner automatically. Give it a moment if you're writing that down. But it's just multiplying those 4 terms together. That's all these steps are here. It's just multiplying those 4 terms together, knowing that when you have imaginary conjugates, they're going to cancel each other out and end up with a real polynomial without any imaginary parts. There's no imaginary terms in that real solution. Okay, so they end up doing all the same thing, multiply the factors. There's all the steps of them multiplying all these factors together to get the x to the fourth minus 2x to the third plus 26x squared minus 50x plus 25. That's the exam answer we have on our notes right there. Okay, there you go. 0 is 1 with a multiplicity of 2. And then, here's another example where it takes negative square root of 7 times the square root of 7. Negative square root of 7, square root of 7, and 4. You just set it up as x plus the square root of 7, x minus the square root of 7. And the square root of 7s at some point, when you get them multiplying them together, you'll end up them going away and ended up with just a real x to the third, x squared, x, 28. No square roots left in there. Okay, lesson summary. Determine the possible rational zeros. Determine the possible positive, negative, complex zeros. Do all of that. Determine the zeros by using synthetic division or the remainder theorem to figure out what it is. Once you have one of them factored out, you now have a depressed equation you can use to continue finding the other ones. And then when you get it down to a quadratic equation, hopefully you can just solve it at that point by factoring, by quadratic formula, whichever methods that you're most comfortable with. And like this one had the plus or minus I as solutions. And going the other direction, if you have the roots, you can turn those into the factors and multiply them together to get the original polynomial. The only tricky part of that is just remembering if there is a complex root, an imaginary root, you have to have its partner. 3i would also be -3i. -3i is also a root. They come in pairs. Step 2, multiplying all that together. And then if you have square roots, you just set up as x plus the square root of 2, x minus the square root of 2. And then multiply those together. All right, there are a couple of pages of sample problems. So if you're confused by this, you think, man, I don't know if I can do all that, here's where you want to try it. Try this. See if you can come up right here. Determine the zeros of each polynomial function. X equals 2. What happens if I hit C explanation? Does it show me? Oh, there's going through all the steps to figure out the zeros. All right. When you try to write a function with these roots, so it gives you 4 of multiplicity 2 and -1. So that's going to be 4 of multiplicity. It's going to be 2 4s and a -1. So it's going to be some x to the third equation. Just got to figure out which one. And I don't know how many there are there. If I just guess one, let's see. Hey, I just guessed the right one. There's three problems there. 3 problems. And then the next page of practice problems. Do this on your own paper and then check your work. What are the zeros of this? There's the work they did. Use the rational root theorem, Descartes, synthetic division. Oh, there's a next because there's the synthetic division. 8 problems here. 8 problems. All right, let's look at the assignment for this first one. Then we'll go look at our graphing lesson, which should be quicker. Which of the following represents the zeros of this? What are the zeros of that? Basically, you're just solving that to figure out what the zeros are. And I'm guessing 5 is one of them because every one of the choices have a 5. Which of the following represents the zeros of this? Oh, they like those 5s. How about the zeros of this one? Which of the following is a polynomial that has these roots? So this is where you're writing and multiplying them together and figuring out which one of these you end up with. And this one as well. Now this one, they gave you 4i and -4i. So they already told you both imaginary solutions. So you don't have to add one. They told you both of them. Sometimes they get tricky and they just tell you the first one, 5 and 4i. You have to remember -4i also goes with it. But they were nice. They gave you both of them. The quiz, let's take a look at the quiz real quick. Quiz just covers up to this part that we've done. How many questions are there? What's the quotient of this divided by this? You can do that. Well, that you have to do long division. You can't do synthetic division because it has a 4x. Remember, synthetic only works with like x minus 3. It doesn't work with 4x minus 3. So this is a long division problem. Oh, I just clicked that. I didn't mean to select as an answer. I don't know that that's right. Don't know. This one you can do synthetic division. It's just x minus 3. What is a factor of this? So this is what we're doing like in this week's, which is a factor. How many zeros does this have? That's the fundamental theorem of algebra. And describe a graph of the function. Give me the y-intercept, the x-intercept, which is the 0, and the shape, which means the end behavior. Which means the left end is going up to infinity or down to negative infinity. The right end is going down to negative infinity or up to infinity. That's what the shape means. Which way are the ends going? Is this both ends pointing up? Hey, at this graph, both ends are pointing up to infinity. Or both are, or one goes this way. You just got to tell me what it looks like. What does the graph look like? All right, that's the quiz. Okay, graphing polynomial functions lesson. If you want to actually do it on graph paper, it does have some graph paper you can print out. But we have Desmos. You don't have to do it on graph paper. Oh, here's a little video they want us to see. Okay, we'll look at their little. We got a few minutes. We can look at their little roller coaster video.
Meet Patrick. Wild World Amusement Park hires him to build rides. One of the park's main attractions is Loch Ness, an extremely fast roller coaster that goes underwater. There's just one problem though. There has not been much rain lately, and the lake that the roller coaster dips into is drying up. The amusement park owners have asked Patrick to rebuild the section of the roller coaster that goes underwater so that it goes even deeper. First, Patrick removes the section of the roller coaster that goes underwater. Next, he makes a sketch of what the new section should look like. Now, he must direct his employees to build the new piece. But how does he describe a shape that curves up and down like this? These types of shapes are the graphs of polynomial functions. Patrick knows that a graph with two curves like this is a cubic function, so he can begin figuring out the equation to give his employees. The next time you see a function like f of x equals a number times x cubed plus a number times x squared and so on, think of the graph as a roller coaster.
Wow, I love roller coasters. Could you imagine how much it would hurt to be going really fast in a roller coaster and slamming the water? It's like hitting a concrete wall. Water is not soft when you hit it at a fast speed. So, obviously, a fictional scenario there. So, how are the solutions of a polynomial function connected to a graph, and what key features can we identify from graphs of polynomials of higher degrees? So, this talks about how to graph a line, how to graph a parabola. That's review. Without technology, we're not going to worry about that because we have Desmos that we're using. Graphing higher degree. So let's talk about it. A third degree is a cubic function. Let's talk a little bit about translations and graphing functions with our notes. So let me switch over to a note page. And let's talk about what graphs would look like. If we have a cubic function, it's going to be something similar to that. Could be have a lot more ups and downs, but this would be like an x to the third. It would go through the origin. It would go up on the right side and down on the bottom side until we do some different things to it. If we had an x to the third plus 2, remember translations, the way we do translations, if we add a number on the end, all right, plus 2, we'll put it in red. What that does is it moves up here to 2. Everything would go up 2. All right, that's what putting a plus 2 on the end of it does with translations. If it was a minus 2, this would go down 2, right? That's on the y-axis. Instead of going here, it's going to go through 2 instead of at 0. All the points move up 2. If we did x plus 4, now we're taking a number and putting it inside with the x. That's going to move it. Remember, it's the opposite. Plus moves left. 1, 2, 3, 4. It's going to come up over here. And it moved left 4. Left 4. If you want it to move right 4, I don't know where my blue pen went, but anyway. Oh, here's my blue pen. If we have x minus 4 to the third, that moves right. All right, and I'll do, this is up. X squared minus 2 would go, I was going to do it that way, down. This one goes up and down. Okay. I don't really want that to represent the color. So if we want the graphs to go up, we put a plus 2 in it. We're going to go down, do a minus 2, goes down 2. Left and right is the opposite. Minus actually sends it to the right, to the positive x's. plus 4 sends it over to the negative x's like this. And let's talk a little bit about what we can expect. If we have x to the 4th degree, the graph is going to look something like it looks a lot like x squared, but this is a little flatter down here. And again, if it's like x to the 4th minus 2x to the 3rd plus x squared, minus 1, something like that, it could look like something like, something weird like that. But here's the key. Here's the key when it comes to reading graphs. If we have x squared or x to the 4th or x to the 6th or et cetera, et cetera, et cetera, even numbers, the left end is going to point the same direction as the right end. Both ends are going to point the same direction. If it's a negative x squared, negative x to the 4th, negative x to the 6th, et cetera, et cetera, et cetera, then both are going to point down. This is the first term is a positive here. So let's kind of graph that up. With even, if it's positive, it's going up. If it's negative, it's going down. And this is the largest term. Like on this one, it's got a 4th, a 3rd, and a 2nd. Everything is driven by the big boy, whoever's largest. Just because this is the 3rd doesn't matter. X to the 4th is the largest exponent. That means both ends are going the same direction. If it is odd, which means it's an x or an x to the 3rd or an x to the 5th or an x to the 7th, et cetera, et cetera, et cetera. Going to go down on the left and up on the right, assuming these are all positive coefficients. Down the left, up on the right. Where in the other case, if it's a negative x to the 3rd, negative x to the 5th, negative x to the 7th, the left side is going to point up and the right side is going to be down. If these are negative. So it all depends on, first off, is this an even or an odd number as the coefficient? And is it a positive coefficient or a negative coefficient? If it's even, guaranteed both arrows are pointing the same direction, either both up or both down. If it's odd, it's always going to be one going up and one going down at the ends. At the ends we're talking about. It's just which one goes up, which one goes down depends on whether it's positive or negative coefficient. Positive or negative coefficient. This one's easy. If it's positive, they're both pointing to the positive. If it's negative, they're both pointing to the negatives. If this one's positive, the right end goes positive. If it's negative, the right end goes negative. So if you think about that, the right end always points the direction of whether it's positive or negative. Positive, these are both positive. The right end always points up. These are negative. The right end always points down. So that's one of the big things on graphing is understanding how that works. And this talks about the plus C, minus C, and all that kind of stuff. If we multiply, put a number in front, that just makes it skinnier or fatter, right? So graph this function. So it says f of x equals x plus 2 to the 3rd. So we're going to go here and say f of x equals x plus 2 to the 3rd. Oh gosh, I didn't do it. To the, all right, now what do we expect it to look like? X plus 2 to the 3rd. So this is to the 3rd power. So that means the left side is going to go down, the right side is going to go up, right? And there's a plus 2, so it's going to be moved left 2 from the origin. So let's put this 3rd power. Oh, see, it go left 2 because of the plus 2 in parentheses. And since it's third power, the right end goes up, the left end goes down. So it goes down, goes up. We knew exactly what that would look like before we graphed it because we saw it was a third power, and the +2 moved it to where it's over here instead of the origin now. Let's see, they're doing it manually, but there it is. Let's take a graph of a quartic function, which is a fourth degree function. So if we want to look at a fourth degree, I'm going to take off the stuff inside there. Oh, it didn't do it as an exponent. See, it looks a lot like an x squared. Like I said, it's just a little flatter. Equals x squared. It's flatter and it goes up faster. You look, take it off, see how flatter it is? If I exaggerate it big time, like the 14th power, look how flat it is now. It looks like it's almost goes straight across. But it goes up super fast compared to like an x squared. So the bigger the number there, the faster it goes up, and it's just flatter on the bottom there. Just like that. You might be thinking the graph of a quartic function looks like a parabola. You're right, except it doesn't exactly. You can graph this by hand. We're not going to worry about graphing it by hand. Will most cubic and quartic functions be as simple to graph? Well, yeah, if we're using, she's showing how to do it by hand. We're not going to watch that video. It says, without using technology, so without graphing at all, describe the end behavior. All we have to know is this is x to the 23rd, and it's a +4 coefficient. So what is the end behavior of this graph going to be? Think about that real quick. 4x to the 23rd. 23rd is an odd number. But 4x to the 23rd, that means one end's going to be up and one end's going to be down. What's the coefficient? It's a positive number. It's a +4. It's a positive number. So that means the left side of our graph is going to be pointing downward and the right side is going to be pointing upward. That's all we have to know. It's all it's asking. What is the end behavior? Let's check. It's not necessary to graph it, but look at the degree. The degree is 23, an odd number. That means that the ends will continue in opposite directions. And because the leading coefficient is positive, the left end will go down and the right end will go up towards the infinity, positive. And here is actually a chart. This is kind of what I wrote on paper. I just did it with more symbols and they did it with more words. Positive, if it's an odd degree, it's an odd function. One goes up, one goes down. If it's positive, it's left, down, right, up. If it's negative, left, up, right, down. An even degree goes the same directions, either up or down, depending on whether it's positive or negative. So this is a nice little chart. If you don't like the way I did it, you can do it the way they do it in Buzz, as long as you have something in there to understand what happens in your notes. So with technology, it says graph this function, -x to the 4th, using technology, and describe the end behavior. You copy it, it doesn't get the 3rd power, 2nd power, 4th power. What is the end behavior? The left end and the right end both point towards negative infinity. They both go down. Left and right both go down. Because it's an even number, the largest coefficient's even, so we know they go the same direction. And it's a negative coefficient, so we know that direction is down. The ends of the graph will continue down. Yep, you see that. Graph this function, -3x to the 3rd with graphing technology. Describe the end behavior. It's a negative and 3rd power. So that means if it's negative for an odd, the left end is going to be up, the right end is going to be down. Left end up, right end down. But don't complicate that. It's really just as simple as looking at the exponent and is the coefficient positive or negative. The x-intercept is the solutions. This has 3 solutions. They're not nice. Oh, wait a minute. Is that one? That one's not touching. That's not a solution. This has 2 solutions. And since it's a 4th degree, we know the other 2 solutions must be imaginary. Well, there is a solution at 0.708676 and 1.64551. Those are the solutions. The other two are imaginary, since the fundamental theorem of algebra says there's 4 solutions. Let's see what we got here. Using graphing technology to find the x-intercepts is not hard to do. It crosses, this one crosses a -1, +1, and 3, so you know those are the solutions. And they checked it with the remainder theorem, with the equation, and found the remainder is 0 if there's 3 points. Page 4, about out of time. Key features. Average rate of change. That's one thing we haven't looked at. Increasing versus decreasing minimum maximum. All right, let's talk about that real quick. Average rate of change is one that really, for some reason, seems to give a lot of people trouble. If I have a graph just like this, and whatever this graph does, let's say it goes something like that. All right, so it goes through, here is, I'm adding the points. So this is the point 2, 2. See, there's a 2, there's a 2. So this is the point 2, 2. And it goes to the origin right here at 0, 0. And then wants to know what is the average rate of change from x equals 0 to x equals 2. What's another word for average rate of change when we're talking about math and graphing? There's another word we use for that. It's one word for average rate of change. That word is slope. Anytime they're asking you the average rate of change, you're asking the slope. And you're like, you look at this and like, well, I don't know. This goes down over here and back up over here. See, that's not a consistent straight line. No, the graph is not, but I'm just asking about these 2 points. What is the slope from here to here? The slope from here to here, you can actually draw a straight line if you want to. Well, you'd have to put it on paper, but I'm like, it's really taking an imaginary straight line from that point to that point and saying, what is the slope of that line? What is the slope of that line? That's what it wants to know. Well, you can always, if it's on a graph, you can go 1, 2, 1, 2. The slope rises to and runs to. That means the slope is 1. The average rate of change is 1. Because it goes up 1 over 1, up 1 over 1, or up 2 over 2. It just wants to know the slope between those 2 points. And then it talks about maximum and minimum. This is a relative maximum. This is a relative minimum. Because in this part of the graph, nothing's higher. And this part of the graph, nothing's lower. We can talk about that in Algebra 2. It's kind of a review. Increasing and decreasing. As you go from left to right, this graph is increasing from forever down here up until right there. And it's also increasing right here. So the Y's are getting bigger, bigger. Now here it stops increasing. It's no longer increasing right there. Now, for this small section right here, it decreases. So where is it increasing? All we care about is the x's. 1, 2, 3. This is x equals -3. So increasing from negative infinity up until -3. See, from all the way down here, it's up, 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 up until -3. Then it stops increasing. And then when it gets to 0, it increases again all the way to infinity. No, yes. Where is it decreasing? Starts decreasing at -3. It decreases all the way until it hits 0. That's where this graph is increasing and decreasing. And we can see that. You just got to know how to mathematically describe it. And it's all based on the x's. the x from negative infinity all the way to -3, and then here at 0 all the way to infinity. It's the y's going to be getting bigger that whole time. The y's are getting bigger that whole time. So that's what this is looking at. The x. When the x is negative infinity all the way up till the x is -3. It's increasing. At -3, it's not increasing or decreasing. That's where it's flat, right there at the top. That's why we put parentheses instead of brackets. That's what this is talking about. Increasing, decreasing, maximum, minimum, translations, lesson summary. It'll kind of go over all of that we just talked about. End behaviors, average rate of change. You can use that slope formula that you learned back in Algebra 1, y2 minus y1, x2 minus x1. Maximum, minimums, increasing, decreasing. How do you shift it left and right, make it skinnier? Let's look at the assignment because our time's about up here. There are some practice problems. You do have 2 pages of practice problems. You can go there. Given this function, what is the resulting function when you shift it to the right 1 unit? So there you've got to substitute x. Do you want to put the x in with the x to shift it right 1? Do you want to add 1 to the end of the function? Do you want to subtract 1 at the end of the function, or do you want to put an x minus 1 into the function? Remember, it's just the opposite. Right 1 would be, I want an f of x minus 1. I don't want to put it afterwards. That'll make it go down. That'll make it go up. Oh, if this is calculate the average rate of change, you can either graph this and look at the slopes between -1 and 1, rise over run between those 2 points, or you can substitute -1 in here and substitute 1 in there and find out what the difference is. What's the end behavior of a 3x to the 32nd? That's an even number, so you know they're going to go the same direction. Are they both going to go up? Are they both going to go down? All depends on the coefficient. Which part of the function indicates that the left and right ends point in opposite directions? How do you know that? Look at this. How do I know they're not going to be pointing the same direction? And then graph this function and identify when the graph is decreasing. When does it decrease? Graph that and say, when is it going down? We are out of time. It is 10:30. We had a lot of stuff we're throwing in. The graphing part, use Desmos all you can and look at it. If you struggle with any of this, this is an 8-day Friday, so I'll only have class Thursday. But come see me Thursday if you need help with any of this. I'm happy to go through it in a little slower time where we got a little more time to play with it. All right, guys, have a great week. We'll see you Thursday or next week.